Hi, my name is Youngseok Kim from KAIST, and I'm happy to share my work today. The title of the paper is CRN, Camera Radar Net for Accurate, Robust, Efficient 3D Perception. I'm going to start the presentation with the background and motivation. Currently, LiDAR is the most preferred sensor for autonomous driving thanks to its dense and precise data. However, the high price and reliability of LiDAR is not suitable for a commercial vehicle. On the other hand, camera and radar are already widely used for ADAS, but its performance is very limited to non-complex environments such as highway. So in this work, we aim to achieve LiDAR-level performance with low-cost camera and radar. But why the camera-radar fusion is not easy? As can be seen on the left, the camera and radar have very complementary properties. For example, radar provides accurate distance measurement in range direction, and camera has dense and precise resolution only in angular directions. Because the advantage and disadvantage of sensors is very clear, we have to handle these complementary properties effectively. In molecular 3D perception, we have to transform the information in the 2D image into the 3D space. However, the performance of the molecular depth significantly drops on moving object or small object, which is very critical in driving application, and we aim to improve this by using radar. But radar has some technical challenges. First, radar measurements are sparse and ambiguous, so not every radar measurements are beneficial for fusion. And moreover, pixel-to-pixel mapping is not available in radar because there are multipath problem and lack of height information. To this end, we have to treat radar points adaptively. The goal of the proposed method is to generate a reliable bird's-eye view feature map that has rich semantic information from camera and accurate spatial information from radar. So we can utilize bird's-eye view feature map obtained by Fusion for multiple downstream tasks, such as on 3D object detection, tracking, and segmentation. In summary, our method achieves LiDAR-level performance, and it maintains robust performance in sensor failure cases. And finally, it can be run in real time. And I will not go into details, but briefly introduce the key ideas because of the time limitation. And please refer to the paper for detail. Our first key module is radar-assisted view transformation. A view transformation module transforms 2D image features into 3D space by estimated depth distribution, but it becomes less accurate as object becomes far, as highlighted by a red circle. To make this view transformation process more reliable, we proposed a radar-assisted view transformation module to fully utilize both depth distribution and radar measurements. Our proposed module can effectively overcome the problem of radar, such as noisy measurement and lack of height information. After obtaining both image and radar feature map on bird's eye view, we further aggregate feature map to handle spatial misalignments between camera and radar features. In this way, we can benefit from both camera and radar for semantic and localization information. As a result, our fused bird's eye view feature map can have a rich context feature at an accurate position, as can be seen on the right bottom figure. This video shows the comparison between multiple methods. As shown in the video, ours have more accurate localization on faraway object. And moreover, camera and radar fusion shows more robust performance in the rainy scenario compared to the LiDAR. And finally, we can find that the localization becomes more robust under low lighting condition compared to the camera method. As shown in the left, the proposed method has a good speed performance trade-off and ranked the first place on the nuScenes object detection benchmark among camera and camera radar fusion. And also, we validated that our method on tracking and segmentation task, and we confirmed that the proposed camera and radar feature map obtained by Fusion can be generalized in many downstream tasks for autonomous driving. I want to conclude the presentation with two takeaways for camera and radar fusion. And I hope our paper will inspire future research on camera and radar fusion. And please check out paper for details.